Oh, so today we're going to talk about some terminology in the electricity. Okay, so let's talk about charge first. So charge, usually using Q or Q, okay? So it can be positive or negative. And by charge here, normally they are static. So they don't move, okay? Normally, yeah, static charge. But they can, they can move, right? Normally, we don't have it moving. So, and then the unit is coulomb, also shown as C, okay? And just keep in mind, 1C is very large, So 1 electron's charge, the special charge called elementary charge. Right? It's the charge for 1 electron or 1 proton, okay? And they are only 1.6 times 10 to the negative 19 coulomb. So you can see how big is 1 coulomb, right? Okay, let me change the color a little bit. And then between 2 positive charge, so this is being acted on, pushed by this one here. So I'm going to call that one F, okay? And this one is pushing this charge this way, right? Because they are repulsive. Okay, so I'm going to call that one F prime. All right. And then if it's minus and minus, then it's similar, right? Still repulsive, right? So both are repulsive. If you have plus and minus, then it's attractive, right? So this will be attractive. Okay. So keep in mind plus, right? In a lot of times, this plus just means that we have more proton than the number of electrons. Okay, that's all it means. So let's say if you have positive, 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 and then outside you only have 1 negative, another negative, then this one here will be plus, right? That will be a plus charge. Okay, so that's the charge. And let's move on to the second terminology, still for electricity, right? So we're going to talk about electric force. So usually we have a small e, E for electrical, or electric. So also called Coulomb force. Also called electric force. Okay, sometimes they also call this electromagnetic force. Sometimes it's also called electric static force. If the charge is not moving. So just, there's a lot of different names. So this electric force, the formula goes, you have K, and you have Q1, Q2, and then divide by R squared. So this is called Coulomb's law. Okay, and let's talk about the unit here. This is Newton, and this is Coulomb square. This is meter square. So then this one here would be Newton meter square divided by c squared, and that's equal to 9 times 10 to the 9. So it's a constant. It's called Coulomb's constant. Coulomb's constant. Okay, so F, it's a vector, right? It's a vector here. The electric force is a vector, right? So it has direction. So it has magnitude and direction. Okay, so let's give you one example. You have one here, call that Q. So that's, I'm going to call this one here. This is the charge that create a field, okay? Charge create a field. and electric field. Okay, if you put a test charge here, okay, let's say that's also a positive, positive, and that's the test charge. Okay, I'm changing color. Okay, so in this case, right, the electric force on this one, this is my system, it's going this way, right? So that's my FE due to this one here, okay? So this FE is equal to E, which we'll talk about later, electric field, times, right, times this Q here. This Q, let's say, let's call this one Q1, times Q1, okay? And this one is Q, right? All right, so this electric field, due to this one here, would have a force pushing this one here, this direction, right? And this is kind of like you draw the line, and that's your direction right there. So you talk about direction, there is a direction associated with electric force. Okay, so let's move on. I'm going to clear that. Now we're going to talk about electric field. So E, it's a vector, right? It's called electric field. And the unit is Newton divided by Coulomb. Okay, as you can see, F is equal to E times Q, right? So then this is Newton, this is Coulomb. So then this is Newton divided by Coulomb. So electric field, right? So if you have a charge, Q, then surrounding the space nearby this Q, right? This is the charge that creates the field, okay? Charge that creates the field. Or forms the field, right? Create the field. Create an electric field, okay? Electric field, it's a field. So then there's no, if you don't have a test charge here, but there's still is an electric field there. And this electric field, if this is positive, this electric field must be going this way, away from it. And this E is equal to K times Q divided by R squared. And this is the distance R here. Okay? So if I have another one here, let's say I'm looking at this point, there's no charge right now, okay? Just the electric field. Then this one here, it's going to be R prime. And R prime is larger, so this E will be smaller. Let's call this one here E prime. So this E prime in magnitude will be smaller than E, okay? And Q, let's always just make it positive, so then you can then compare the magnitude. So E prime is equal to KQ, same charge that create the field, okay? So divided by R prime, and be careful with, there's always a parenthesis and then square, right? So R prime is larger than R, right? So then E prime must be smaller than E. So that's the electric field, right? So let's continue with electric field a little bit. So if I have a negative charge, then my electric field is defined as going toward it, okay? And the distance here is still R. And the electric field here, and let's say this is the charge that form the electric field. You don't need to have a charge there. Then the electric field already exists, right? So electric field exists already, right? As long as this charge, right, that create the field is there, okay? Right. So then this here, this E is the same, but it's different direction because this is negative. So then this is K, Q, only one Q, right? R squared. But this is going this direction, right? In the positive case, it's going away from it. Right? So that's electric field. Okay, so next one, we're going to talk about electric field line, okay? That's different from electric field. It's the electric field line. Line with an S, okay? So if you have a positive here, and then all the electric field line, it's going away from it. Why am I drawing this many? because I want to show something else, right? So there's more on this direction too, okay? But it's all going away, right? This is positive. The electric field definition is going away from the positive to an electric field line, okay? Now, let's take a look at the density. See that the density that nearby the charge gets more crowded. You see that? This length is smaller, right? But the number of line is the same, right? But now if you go away and you come to here, see that? The number of line is the same, but now your length is longer, right? So you can see this on here, the density compared to here, the density, right? So this density prime is less than the density. So what does that mean? It means that this one here means that indicate the electric field is larger right here compared to this one here, the E prime. Okay, and as you can see, this distance here is going to be R prime, and distance here is going to be R, right? So then the E must be larger than E prime because the R is different. Okay, so that's electric field line, and let's just continue on the electric field line. So electric field line, if you have positive and a negative, so when you draw it, an electric field line, let's draw one of them, right? So at any single point, let's say this point here, right? The tangent at that point, right? So this is tangent at P, okay? At this point P, this is a point, okay? Point P, at the point P. Tangent at the point P indicate the direction, of the E. Now, the E field, electric field at that point, at P. Okay, so this P has electric field, okay? And this electric field is influenced by this one here and also that one there. So that's, we draw this one here. Due to this one, the electric field is going this way. So that's called that E1. Due to this one, the electric field is going toward it, right? So it's going like this. And slightly smaller because R is longer, this R is shorter. So this is E2. So then you use the parallelogram, right? So then it tells you that this electric field must be going like that. It's slightly upward, right? Slightly upward. You can see this is the electric field that I drew. See that? This is a resultant. Okay? So the tangent at point P indicate direction of E at this P. But in this case, I have Q1 and Q2. Okay? So Q1 give you E1. Q2 give you E2 at this point P. So then the results in this resultant, right? This is a resultant E. So it's a combined, right? Resultant means combined. It's a combined E at that point. Okay, so that's electric field. Let's continue. Now we're going to talk about flux, right? So flux, it's similar to the Q, right? So if you like, oh, what's flux, right? This is electric flux. So I normally just using small e, okay? You can also using capital E if you like. Electric flux, it's very similar to the Q, okay? How is that so? So electric flux is defined as, right? Defined as Q divided by epsilon 0, okay? And epsilon 0 is constant here. And this constant is equal to 9 times 10 to the negative 12, okay? And that's Newton meter square and then C square, okay? So that's the constant. And it's called permittivity, double T. And in Chinese, it's called 容积率. Right? So it has to do with some kind of capacity, okay? Some kind of capacity. So permittivity of free space. So when we say free space, it's talking about air right now, okay? Air, vacuum, right? So this epsilon is dependent on the material. And this material right now, the electric flux is in the free space. And this free space is the air. So it's having this particular constant. As long as you have the air or vacuum, that constant doesn't change. So you can see when you know the charge, right? And this charge is an enclosed charge, right? And this phi is, you sum it up, the E perpendicular times the A, right? Over a surface, over a closed surface, over a closed surface. So this closed surface can be this sphere's closed surface, right? And this closed surface, the A is equal to 4 pi r squared, right? According to a sphere, right? This is for a sphere. Okay? Right. So if you started with, right? So if I put this in, and I'm just going to call, this is always perpendicular. So then this is equal to E times 4 pi r squared, right? Okay, so then that's changing that form. So we have E is equal to, I'm going to divide this over, right? So 4 pi r squared, and then epsilon 0, right? And then Q. Okay, so look at this here. Look at this tiny guy right there. Well, not tiny guy, 4 pi epsilon 0. Okay, so that one over 1, right? So 1 divided by that. So you can see that E now is equal to KQ divided by R squared. Because K, it's also Coulomb's constant, also defined as 1 divided by 4 pi epsilon 0, right? Okay, so you can see this tell you, this one here is the Gauss law. So Gauss law is very general, right? It's very general, very general for any surface, any closed surface, right? But Coulomb's law, it's in this case, it's all talking about isolated charge, and you're using the sphere concept, right? So this Coulomb's law is using Coulomb. So this is part of the Coulomb's law right there, right? Okay, so Coulomb's law is F and then E times Q, right? Okay, or you can say it's the K Q1 Q2 divided by R squared, right? So this is part of that Coulomb's law definition, and this is a special case. So that's a special case, and it's over a sphere symmetry. Okay, sphere symmetry. Right. So that's why we can say A is equal to 4 pi r squared when we specialize into this surface here. All right. Okay. So now we're going to continue with some more definition. So we're going to define something called surface charge density. Along the same line of Gauss law, charge density. So sigma, right? So sigma is equal to Q, so charge, right? And it's the density, so divide by the A. And that's the surface, right? So this is A, this is surface area. Okay? So if we define that, and now we go back to the Gauss law, right? So E, right, times A, right? Assume they are perpendicular, then that's equal to E times A equal to Q, right? Q enclosed divided by epsilon 0, right? Right. If you move this over, then E is equal to, right, Q divided by A, which is then sigma, right? And then divide by epsilon 0. So then that is your another way of defining the electric field. It's this density term divided by this permittivity, which is a constant. So if you want to apply this, this is actually quite general, right? So if you know your surface density of the charge at a certain area, let's say you have a charge right there, Q, and in some of this area right there, right? So if you know the A, right, and this A, and then you know this is the charge, right? So this is enclosed by it. And then, you know, if you integrate it over, right, then it's your total area now. And then the enclosed charge is this one here. Let's call this one Q, E, and C, right? So then you can figure out the E at this point, right? The E at this point. Okay? And at a different point, you have a slightly different density. And then so then that would define that particular E at that location, which may be different compared to this surface here. And your E may be a little different, right? The E prime would be here. Okay? Yeah. So that's the density will be different. Yeah. Because your area here, you know. All right. So that's all. We're going to stop there. Okay. And until next time, bye bye now.